talk today, in the first talk, is just a basic introduction or background to what is radio astronomy. Who will tell me what is radio astronomy? Yes, the youngest in the audience. Yeah, go ahead.
Radio astronomy is the pulsar gives energy and that energy goes to every gadget.
Okay, all right, good. And you saw that outside the demo, with the pulsar giving energy and being caught by the telescope? Yes, okay, that is certainly part of radio astronomy. Okay, so basically what we'll start with is to understand how radio astronomy is different from a normal optical astronomy. Okay, so and then we will talk a little bit about what is the basic idea of a radio telescope, how they work, how you get signals from the objects in the universe, what is special about the radio telescopes, and then we look at one example of that, which is our own radio telescope, the Giant Meter Wave Radio Telescope, which is built in India and run by our institution. And then we will talk about what is there in the future, which a science exhibition has been organized to talk about what are the large next generation projects in the different branches of science. And the square kilometer array, which is a radio astronomy project, is one of them, which you will see on this big illustration which is there on the side. You should later on go search where is SKA and what is it studying, whether pulsars are being studied there or what is being studied. You see that big picture on the side? Later you should go and have a look at it and see that how these different projects are going to be studying different aspects of the universe. Okay, so like I said, wherever you feel free, you can stop and ask a question and we can have a discussion rather than me just talking and in the end all of you just either nodding or not nodding or whatever. Okay, fine. Okay, so let's start with this. So as we know that from astronomy is called the oldest science, right? And for the simple reason that once human civilization sort of settled down, man learned how to be self-sufficient in terms of either growing food or being able to have a reasonable life. His curiosity has always been there, and so the first thing in curiosity is you look up and you see all these faraway objects in the sky, right? And now what happened? Okay, and then you wonder what is up there, right? And that was the natural curiosity, and that's when people just started and trying to make constellations in the sky and try to understand the stars and objects in their own way that they could at that time. And obviously it started by using our eyes to be able to see the objects, and that is one of the most important things, that in order to see anything you need to have the ability to detect that signal. Okay, and our eyes have the natural ability to detect optical light, and so anything which is there in optical you can see without needing any help for detecting the signal. And so that is why natural thing would be to first see whatever is visible in optical. So you see the stars, you see the moon, and you see the differences in the different objects, and you start wondering what is there, right? So that is how it started, and even with naked eyes, people made a lot of progress to try and understand various things. For example, they could make out that there are different objects, like what are now called planets. They behave differently than what are called stars, right? And then this all could be done with naked eye, and to understand the daily motion of the objects and the variations in all of that, a lot of it could be done, including detecting some supernovae. There are historical records where people with naked eye have detected these events and recorded them. Okay, so all this was going on, but it was all suddenly revolutionized when this person who did what? Okay, so who's this person who went from naked eyes to something better? Huh? Yeah, Galileo, right? So he, what he did was this optical telescope, which was recently invented. He said, let me turn it towards the stars. So he's not the one who invented the telescope, and there's somebody else who made the first telescope. But he is the person who first said, hey, why shouldn't I turn this upwards and see what happens? What do I see? Okay, and when he did that, he found that there's amazing more things that you can see compared to the naked eye, right? And we'll see that in a minute, the moment the connection starts working again. And so that completely revolutionized astronomy, because now you could see a whole lot more. And that is what you have to understand. Why is it that you could see a whole lot more using the telescope, which is still dealing with light waves, compared to our naked eyes? So anybody who wants to say what is it that makes a big difference between naked eyes and the telescope?
More amount of light.
Collecting more amount of light. So how does that help?
You can see fainter objects.
Yeah, you can see objects more clearly. You can see fainter objects, right? Yes, you have your hand up.
So you can see it more clearly because stars are very big, and if you see with your naked eyes, they look like just this much, but with an optical scope, you can see it properly.
Okay, okay, that's a debatable question, whether if you put an optical telescope to a star, as you said, it looks like just like a point, does it become much better or not? That we will come to in a moment. But certainly you can see more objects, you can see fainter objects, because it is collecting more light, right? So it is like this, that when you go into a dark room, you dilate your pupils. What does that do? It opens the aperture in the eye. So the eye is collecting more light. It needs that because it is very dark, and you need to collect as much light as possible to see objects in the dark. But when you go out into the bright sunshine, your eye pupil closes and reduces the size, because you don't need now that much light in order to see things. And so that is how, in some simple way, you have a control amount of light. But here these apertures are much bigger than what our eye's aperture is, so you can collect more light and see fainter objects, and in some sense they give you magnification. Okay, and then we'll come back to that in a minute. But since the time Galileo made the telescope, there were many improvements in the optical telescope all the way through the ages. When Newton made his simple telescope, then Herschel, and then these more modern telescopes up to these large structures. And obviously you will see one clear thing here, that they are slowly becoming bigger and bigger, right? And so that's the question, that why is bigger better? And one of those you have already answered, that if it is bigger, it will collect more light. You can see fainter sources, okay, just like when you dilate your eyes to collect more light in when you are in dim light condition, and therefore they are more sensitive and they can see more objects in the universe. But there is another thing, that the bigger telescope has a higher magnification. And what does magnification means? That the same object which is there, it will make it look bigger. So bigger, how does that help? So for example, if an object has two bright spots on it, then when the object is looking small, the bright spots will merge and they will look like one spot. The moment you make the object bigger and zoom in, then you will start separating out those two bright spots, and you will start seeing them at some point as two separate spots of light rather than some merged object, right? So this is when you take any image and you say, let us zoom and see. So when you zoom, then you can see more detail in the image, okay, in the same object. And that is what is called magnification, and it is also called resolution. So it so happens that when you have the bigger size of the aperture, you get a higher resolution, and you can then see nearby objects more clearly. Okay, and it so happens that both of these, the sensitivity, that is the ability to see fainter objects, and the resolution, that is the ability to separate out nearby objects, are both dependent on the size of the telescope. So the larger the telescope, clearly this you can imagine, right? The amount of light you collect should be proportional to the area of the telescope, right? So, and the area goes as square of the diameter of the telescope. So the sensitivity increases as the square of the diameter. On the other hand, the resolution goes inversely as the size of the telescope, and it also depends on this quantity, wavelength of the radiation. So wavelength of radiation, we understand that when you are looking at light, it has a certain range of wavelengths, right? Who will say roughly how much it is? Anybody? Right, so roughly that, so or 4,000 to 8,000 angstroms, right? And we'll come to that what is beyond that in the frequency range. So if you increase the diameter, the resolution becomes better, and here smaller means that is the separation which it can resolve. So the smaller the separation it can resolve, the better is the resolution, and it becomes better as you increase the size of the telescope for a given wavelength. Okay, and so this is important because we will see this when we come to radio wavelengths, that the problem becomes different. Okay, so we'll see just two examples of this. So this is the improved resolution. So when you look at the moon with your naked eye, you will see something like this, right? You can make out dark patches. So you when you went to the terrace, did you see the moon? Both of you, right? So and then you saw in the telescope also, right? So tell me which, when you saw it with your eyes, it will look something like this, right? And you can see some dark patches, right? And then they say there is something on the moon, right, which you are supposed to look for. But if you look with a simple telescope, you will see something like this. So you can see that these two are dramatically different. It is now being able to resolve different objects which you could not make out here, separate them out. With a slightly bigger telescope, this will give you even more resolution. So now this part you can see now more clearly, that there is one central crater here, and then there are smaller craters here which you can start seeing in detail. It's like zooming in, right? So this is resolution. And we'll show one more example of this. How many of you know about Andromeda Galaxy? भैया ये आपका बार बार ऑन ऑफ हो रहा है अभी भी? Where is the connection? It depends on where the problem is in the contact. So how many of you know Andromeda Galaxy? Okay, yeah, why don't you say? What do you know about Andromeda Galaxy? Yes, so it's one of our nearby galaxies, and it is also interesting because if you go to some place where the sky is very clear, you can just about make it out with your naked eye. Okay, it's probably the only galaxy outside our Milky Way that you can just about detect with the naked eye, but not, you need to go to some place where the sky is very clear. And so you will see it like a small fuzzy patch with the eyes in the constellation of Andromeda, which is shown here. And now if you take one of the simple telescopes and look at it, it will start looking like this. Now you can make out this fuzzy patch a bit more clearly. Okay, if you use a slightly bigger telescope, it will start looking like this. And now you can see that you can start seeing the structure, and you can see that it is a galaxy. Something has happened to this picture, but with a bigger telescope now you can clearly see galaxy. You can see many of the fainter stars near it, and you can make out more detail. So both the faint objects are now more clear as you go from here to here, and you are able to resolve and then see close by objects more clearly. Okay, so this is what illustrates the power of the telescope. Okay, Now let us ask what happens when you go beyond the light waves. Okay, as you know that light waves are part of a large electromagnetic spectrum, right, which goes over a range of frequencies. The lowest is radio waves to the highest, which goes up to gamma rays. Okay, so if you look at this is what it looks like, the entire electromagnetic spectrum, where the lowest frequency or the longest wavelength is radio waves. Then you go to microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. And this visible is the one that we were talking about, because our eyes can detect the radiation. Our eyes cannot detect the radiation of any of these other wavelengths, and so we have learnt about it from different techniques. Okay, and this is just shown to scale the different objects whose sizes sort of are comparable to the wavelength. And so what happens then is that you can ask the question that can the same object really be studied by different wavelengths? So for example, you know that you can study the different objects in this room using optical wavelengths, because they either emit light or they are reflecting the light and you can see them. You can ask, is any of them emitting infrared? Okay, and there are certain properties under which an object will emit infrared waves. And similarly, you can ask, can any object be emitting X-rays or radio waves? And so depending on the properties of the object, they can actually be emitting those waves. And if you were sensitive to those, then you could study those objects just like you study the different objects using optical waves. Okay, and you can say, all right, I can detect it, but do I learn anything different about the object by studying it? Okay, and the simplest example is when you go nowadays to the hospital and you're not well, they can do different kinds of treatment, right? So you'll take an X-ray. So when he takes X-rays or he'll do an ultrasound. Okay, so what the ultrasound shows is about your body is very different from what the X-ray shows about your body, right? And so you can see, and which is very different from what the CT scan will show about your body. So there are different ways in which the same object can be studied because of the different properties. So in the same way, the object can be emitting light waves, it could be emitting X-rays, it may be emitting infrared. So if you could study that object in those different wavelengths, you would learn different things, just like the X-ray and the CT scan and the ultrasound will give you different pieces of information which the doctor will piece together and say, oh, X-ray shows this, but ultrasound shows that, therefore this may be the problem, kind of a thing, right? And so you can actually combine this information from the different wavelengths and learn more details about the object and study about it in a much better way. Then there's the other thing, that can some of these phenomena be studied only at one wavelength? So if the doctor wants to understand whether your bone is broken or not, he has to do an X-ray. He can't find that out by doing ultrasound. Okay, so bones will be seen only in X-rays. They will not be seen in these other methods as clearly. Okay, so in the same way, there are certain objects which will transmit or generate only certain kinds of radiation, and so if you want to learn about them, then you have to use that particular wavelength or frequency to study them. And so that brings us to this problem, that how do you study them? So before you do that, I'll just show you an example. So this is back to our Andromeda Galaxy, and so what we saw earlier was this picture, which is the optical picture of the galaxy. It shows stars and other objects in the galaxy. But when you look at this galaxy in different wavelengths, and we'll see later how you can look at it in different wavelengths, then you see that it gives very different looking picture. Just like the body looks very different when seen using X-rays and when seen using ultrasound. So this is all the way through the different things, from the radio to infrared to optical to ultraviolet to X-rays and gamma rays. Okay, so you can see that different parts of the galaxy become prominent at different wavelengths, and different features can be studied more clearly. Okay, and the astronomer will then put together all this information to get the full composite picture of the galaxy, just like the doctor will put together all the different pieces of information to get the best possible picture of what may be happening. Okay, so just to summarize that studying the same object at different wavelengths can give complementary information, and hence a more complete picture can be assembled. On the other hand, some objects or phenomena in the universe can be seen only at specific wavelengths, and we will see a little bit later some examples of that. Okay, so you would say, well, good, if you can observe the universe at many different wavelengths, it will be very nice. Okay, but that is now when we come to the difficulties in doing that. Okay, and one obvious one is that if you don't have the detector, then you can't detect that signal, and so you can't study it, right? And so, as we said, the only natural detector that we have is for optical radiation with our eyes. And so that's the first thing. We need to have the detectors for all the wavelengths, and so this was not there naturally, and then man has learned how to make these detectors by understanding how these things work and how you can make them. So today you have photographic plates, charge coupled devices, radio communication equipment, and so on. So man has learned how to generate and receive radio waves, which was not possible naturally. So second problem is that you may have the ability to detect the signal, but is the signal able to reach you? Okay, and you can ask, well, what is the problem there? So this is simply understood by one simple thing. You all know about the ozone layer, right? What is the importance of the ozone layer? Who will give a quick answer? No?
That's also UV radiation.
Okay. So what? And why is that important?
It causes cancer.
So the UV radiation, if it reaches us, can be harmful. It can do harm, biological harm to the human body. And so it so happens, and where is this UV radiation coming from that is being blocked? From the sun. So the sun, we know sun emits light, but sun also emits UV, infrared. In fact, sun also emits radio waves. Okay, and so it so happens that the ozone layer blocks it. Where is this ozone layer located? Yeah. In the Earth's atmosphere, right? Somewhere. At least that is a reasonable answer. Where in the atmosphere? Okay, we'll see if we are really asked to tell. Okay, so there's something up there which is basically blocking the UV radiation, and if you create a hole there, then the UV radiation will come through, and that's not so good, right? And so, in the same way, there are different obstacles around the Earth which can block different radiation from outside to come in. Okay, and so this shows a picture which shows again the electromagnetic spectrum all the way. Now only radio waves are on this side. So this is the increasing frequency. So these are the lowest frequency radio waves all the way through the infrared to optical, and then this side is ultraviolet, X-rays, and gamma rays. Okay, and what it shows is the opacity of the Earth's atmosphere to the different frequencies. So when the opacity is 100%, means the is completely opaque. That radiation cannot come through and reach us. When the opacity is 0, that means that radiation will easily and freely reach to the surface of the Earth, and therefore you can detect it. Okay, and so you can see, and so these are like windows. Okay, so in this frequency range, the window is open. The signal can come through and reach us. In this frequency range, the window is closed. For some reason, that radiation is blocked and it doesn't reach us. What the reasons may be for different parts of the windows which are closed are different. Some of it is the reflection or absorption in the ionosphere of the Earth. some of it is absorption by molecules in the atmosphere, and so on and so forth. Okay, so it so happens that there are two well-known windows. One is of course optical, because we know that, because you can see the stars through the Earth's atmosphere, though that light comes through. And the other one is a large window in the radio frequency part of the spectrum, and other parts is difficult. Okay, so if you say, well, I have a detector which can detect gamma rays and I want to study different objects in the universe in gamma rays, sorry, you can't do it from the ground. So then you say, how do I do it? So then you have to put that detector or instrument on a rocket, send it on a satellite outside the region which is blocking, and then use it over there, right? So that is why you have space-based astronomy, which is one of the reasons. The other reasons why, even for optical, you want to put, like the Hubble telescope, put it well above the Earth. So wherever you can put things on the ground is easier, right? Your detector, if you have the detector, you can build an instrument which works on the ground, you can study that part of the universe. If you can't do that, then you have to work harder, put the detector up and send it, and then try to study the universe using space-based instruments. So now you can see that given that optical window was anyway open and was being used from the early days, the next window that would become possible to use is the radio window. And this then just had to wait till the detectors were built. And so these detectors we learned how to build as an offshoot of the radio communication technology. So as you know, first man learned that you can generate and receive radio waves. Okay, so you know who was the pioneer in India who did that? J.C. Bose, right? And then of course then we had the corresponding pioneer in Europe who did that. Who's that? Marconi, right? And so they were sort of almost contemporaneous in their lives. In fact, people now recognize that J.C. Bose demonstrated it a few years before Marconi did it. And so you learned how that you can generate radio waves and receive them. At that time, people still didn't know that I could be getting radio waves coming from outside. Okay, and so this discovery that you can actually receive radio waves from objects in the universe happened as an accident. Okay, and many times in science, especially in astronomy, many of these things happen serendipitously. That is, you're trying to do something and then suddenly you find, oh, something different which you did not expect, and a new discovery is made. Okay, so often in science you have discoveries which happen because people are just curious and trying something, and then they find something new and different, and a whole new field starts. So this happened in the Bell Labs, where what they were trying to do is, so when they learned how to generate radio waves, it started being used for communication, like walkie-talkie, or now all the more sophisticated things, including satellite communication and our phones, mobiles, and so on. But the simplest equipments were the equivalent of radio transmitter and receiver, where you can send messages. And they were trying to build something which could communicate across the Atlantic Ocean. So this was the first time they were trying such a long distance. So you need, of course, a powerful transmitter and a very sensitive receiver. Remember sensitivity, right? It can then detect very faint signals. Okay, and so when they were testing that, they found that there was some unwanted disturbance that was coming in the receiver, and was not working as per their specifications or the expectations, which means that it was not going to be sensitive enough to detect the faint signal being transmitted from Europe to America, or vice versa across the Atlantic. Okay, so this person, Karl Jansky, who was an engineer in Bell Labs, he was given this job that you please understand, debug this and see what is going wrong, why this equipment is picking an unwanted signal, and where is it coming from, can we fix it? So he built this kind of a contraption which is actually the first radio astronomy antenna, and his aim was to see where is this unwanted signal coming from. Is it coming from something local nearby, something that some other man-made activity is generating it. And so he built this, and he put this on these rotating platform. You can see the wheels here, so you can turn this in different directions and then see if the unwanted signal is coming from here or from there or from where, and try and understand the problem. What he found when he did this, that the signal was not coming from some fixed place on the earth, but it seemed to be coming from some fixed place in the sky. Okay, so and he was surprised in the beginning, but then he did a careful test and he showed that it is something that is coming whenever the antenna turns and points to some fixed direction in the sky, he would see this increase in the signal level. As you can see these bumps, so as the antenna keeps rotating and coming back to the same place. And you can you can ask, well, how can you tell the difference? Just because antenna is rotated in different direction, it can still pick up something from the ground. But as you know that in the sky, as the earth rotates, the position an object in the sky moves just like the sun, right? It rises and sets. So that if the source is in the sky, its position will keep changing. Whereas if the source is fixed with respect to us on the earth, its position will not change. So whenever the antenna goes back and looks in that direction, it will always see it. But if the source keeps moving, then as the antenna moves, it will find it at different positions every successive round. And that is what he found. And then he was able to pinpoint and say, look, it is coming from this direction, which actually happens to be towards the center of our galaxy. Okay, the Milky Way galaxy. So he then concluded that he was detecting signals coming from celestial objects rather than from some man-made source or something in the electronics or whatever. Okay, and that is how the field of radio astronomy started, by an accidental discovery. Okay, so then once that people learned that you can do this, then people started building more and more sophisticated antennas, which could then look in the specific directions in the sky and try to make images of where you are seeing the signals from. So this was another engineer in the Bell Labs, Grote Reber, who built this kind of, this looks now more like a radio dish or an antenna that we are used to as compared to Karl Jansky's equipment. And this he built in his spare time in his backyard as like a hobby. And he then was able to make a map of the main strongest sources of radio emission coming from outside. And you can see this, it's like a contour map, right? And the contour map shows that one range of directions, like a strip like this, from which most of the strongest radio signals are coming, along with some bright spots in it, in this strip. Okay, so now you can ask, what was this? So you know that we live in the Milky Way galaxy, right? What is the shape of the Milky Way galaxy, roughly? Who will say? A disc-shaped spiral galaxy, right? So first is that it is like a thin disk, and in the disk the structure is like a spiral galaxy, right? So now supposing you were sitting inside that disk and you were looking in all directions, along the disk, away from the disk, perpendicular to the disk, in which directions would you expect to see the maximum number of objects or things in the from the galaxy? Along the disk. So when you do this and you make a two-dimensional map, what will that look like? Will it look like one strip? Yes. Right? So that strip is, as you turn around and look in the plane of the galaxy, you will see maximum number of objects and maximum signal, and as you look away, the strength or the number of sources will fall, and so finally you will see like a strip of thing. So that is what this is. So this is the plane of the Milky Way galaxy that basically he saw, and there of course there will be some very bright objects. It could be some nearby source, a nearby nebula, or in this particular case, the brightest object is towards the center of our galaxy. And so you could actually be able to make a map and show this. Okay, and so that's how the whole field started. Okay, now you may say, all right, what does it look like? So now we'll go to basics of what a radio telescope does and how it works. Okay, so radio telescope is actually in some sense it is in principle and basic ideas it is no different from your satellite dish. Okay, all of you have used a satellite dish, right? Either you have one at home or in your building complex, or you know somebody who has one, right? And what does it do? It receives signal from some satellite, man-made satellite, which is going around the earth, and it receives those signals, converts them into some electrical signals, which are then decoded to give you your favorite TV channel, right? Okay, and so basically there is electromagnetic waves being transmitted from the satellite. There's a different matter where did that information reach the satellite. Somebody has sent it up there, and the satellite is broadcasting it to the various consumers who have the satellite dish, and it picks up the signals, it converts them to electrical voltage signals, amplifies them, and gives them to some device which decodes what the signal is and shows you the signal strength in some way, as a picture, as a sound, video, or whatever, right? The radio astronomy antenna works in a very similar way. Okay, the concepts are very similar, but there is one big difference, and the big difference is that the signals that we are looking for are much fainter than the signals that come from our TV transmitters from the satellite. Okay, and to understand that we will do a little bit of numbers here, but those who have some understanding of a little bit of the technical background, you know that we are receiving, finally when you're receiving a signal, you're receiving energy, right? And the energy is measured in units of watts. That is one unit for measuring energy, right? And watts. And so now you can ask, when something is sending energy, the energy is distributed over a certain area over which it is falling. Like even the TV transmitter, it will have a footprint, right? If you're not in that footprint, then you will not receive any energy, or you will receive very weak amount of energy. So the energy is then quantified as watts per square meter, that is over what area it is spread out. And the energy is also coming in a range of frequencies. So any transmitter and receiver that you have, any TV channel or even your mobile phone channels, they all occupy a certain amount of bandwidth, right? That means some range of frequencies in that radio frequency spectrum that we were looking at. Okay, so if you take this number 10 to the minus 26, okay, watts per square meter per hertz, that is the typical kind of level of the signal that we receive. Okay, now 10 to the minus 26 is a very small number for those who understand what that means. Okay, and it is, if you understand electrical engineering, then it is like minus 100 dBm kind of a signal. But you may say, look, that doesn't make sense to me. But I can tell you in very simple terms that if you take this kind of a signal and you run a radio antenna which is several tens of meters in size, and it is picking up this signal continuously for a few years, it will collect as much energy, which is like a millijoule of energy, which is much less than the amount of energy that you spend if you take, for example, your morning cup of tea. You have to take the water and you heat it. Okay, so you spend some energy in heating water, right? So if you sit down and calculate how much energy is gone into heating one cup of water, it is several thousand times more than this energy that is collected by looking at one source of this kind of a strength by a large antenna, much larger than your satellite dish, and collecting that energy for many years. Okay, so that is just to tell you how minuscule amount of energy is reaching us from the celestial sources compared to any of the other levels of energy that we are familiar with, including any radio communication equipment that we use. Okay, so what does that mean? So that means now you go back to our one fundamental principle, sensitivity. So this is now, these are very weak sources. Okay, and so you know, to see weak sources you have to have a large amount of energy to be collected. So how do you collect large amount of energy? You have to build a very large antenna. So compared, your satellite dish will be a small antenna that is sufficient to collect enough energy from the satellite transmission, but it is not going to be sufficient to collect any appreciable amount of energy coming from the radio signals from outside. So there the antenna is then much bigger, tens of meters, hundreds of meters in size, okay, compared to this less than a meter size dish that you use for the satellite reception. Second is, you may say, look, even if it is getting a certain amount of energy, small though it may be, I can amplify it, right? That is what an amplifier does. I can boost up that signal once I can pick up the signal. Okay, that is generally true, but in any such boosting or amplification, there is always some self-generated noise. So any piece of equipment has its own noise, which comes from the electronics that is used. And if that noise is stronger than the signal that you are trying to pick up, then it will become difficult to hear, right? So if I am trying to speak and there is some background noise, whether it is noise of traffic from outside or people outside are talking loudly, and my sound is very weak, like a small whisper, then you will not be able to make it out because of all the other disturbing sounds that are coming. So in the same way, any electronics that you build, and you can see that in a radio receiver, when you tune the receiver away from the station that you're wanting to listen to, you'll hear a faint background hiss, and that is exactly what Karl Jansky was hearing in that equipment that they were trying to debug. The small unwanted hiss was coming. Okay, and so they thought that it may be from the electronics or from some unwanted source. It turned out to be the very faint hiss of signals coming from the center of our galaxy. So you have to overcome that challenge, otherwise your weak signal will get drowned in the noise. Okay, so for that you have to build receivers and electronics which has very low noise intrinsically. Okay, and then you can ask, well, how do you do this? So then you have to go for the appropriate technology, that how can you build a receiver which amplifies the signal but does not introduce too much of unwanted noise of its own. Okay, and so that is one of the techniques. The other two things are that, you know, unlike your man-made transmission, where the range of frequencies that you transmit in order to transmit, say, one TV channel is some fixed range of frequencies. Okay, and then next to it will be another TV channel with this range of frequencies and so on. That's how you get hundreds of TV channels all coming from your satellite link. But natural sources are not like that. Natural source, when it is radiating, often will radiate over a very large range of frequencies instead of these narrow range of frequencies like the man-made signals. And so if you can collect the signal over a wide range of frequencies, you can get more of the signal. Just like you can get more of the signal if you collect it over a much larger area. Okay, so you can use a very large bandwidth of the observation. So you increase this quantity. So you can see, if you're getting a certain amount of energy, if you increase the watts per square meter, the area, which is this, you can collect more signal. If you can increase the bandwidth, because this is per unit hertz, again you can get more energy being collected. So that is what the first and the third point is. The fourth point is that when you do this, even though you have low noise, there will still be some noise. Okay, and then there are techniques whereby you can suppress the noise compared to the signal by observing the source for a long duration. Okay, and this simple analogy is when you do a short exposure with your camera, then you may not see a very clear image because it did not get enough of the light which you wanted. But if you do a long exposure with the camera and it's a very dim lighting, then it will collect enough light to be able to for the photographic plate or for the CCD to capture the image in a good quality. So here also, if you observe for a long duration, then you can do this. And in all the astronomical sources, the sources are on forever, literally. I mean, the sun has been shining for billions of years and will continue to shine for billions of years. So if you know, and the same is true for almost any astrophysical object. So if you can keep observing the object for long durations, and long durations here can be hours, days, and even a bit longer, then you can collect enough signals so that you can get a more clear image than you would if you had just done a short study of a few seconds or few minutes or something like that. Okay, and since the sources are present and work, active for many thousands, if not millions of years, there is no problem in observing over long duration as long as your instrument works properly over a long enough time. So these are the techniques whereby the radio astronomy tries to overcome the challenge that you are actually signals that you are looking at are very weak. Okay, so this is that first thing, the sensitivity. Okay, and so I will just see the various kinds of antennas which are used to do this, and some of you may be familiar that the simplest one are these dipole kind of antennas, which look like this. And in the old-fashioned TV, when you used to have broadcast TV, then you used to have these simple antennas on the rooftops, which you may still see in some places, which are these kind of Yagi antennas for picking up the radio signals. And then from there you have the more sophisticated reflector type antennas, which is like your satellite dish but much bigger in size for radio astronomy. And the basic antenna is like this, that it will reflect signals, and to reflect the signals properly, the surface has to have a appropriate shape, right? What is that shape? Parabolic shape, right? Because the parabola is the shape where the incoming plane waves will come to a focus at a given point, right? And the focus could be right here when it is a primary focus, or you could put a small reflector and reflect the waves and bring them to a focus over here, in which case it is a secondary focus over here. And at the focus, whether it is here at the primary or over there, you will put a small feed antenna which actually does the job of converting the electromagnetic wave into a into electrical voltage. Okay, so basically that is the first thing you have to do as part of picking up the signal, and that is what is called an antenna in the most general sense. So your mobile phone has an antenna inside it, a very tiny one, which can pick up the electromagnetic waves that are coming from the mobile tower and convert them into a voltage. That voltage is then what the rest of the electronics in your mobile phone will amplify and give you decode the information and give you voice and picture and everything. Okay, and then you take that voltage and you put it through a chain of sophisticated electronics, a lot of amplification, because these are very weak voltage signals and with minimum amount of noise added, and so on. Now the other thing, of course, is that these antennas have to be in general steerable, because you need to look at different objects in the sky, number one. Number two, in order to observe for a long duration any given object, you have to follow the object as the earth rotates, right? So just like if you wanted to keep looking at the moon for a few hours, you have to keep moving because it is moving in the sky because of the rotation of the earth. Okay, and so often these antennas will be on two-axis mount, one which can move it vertically up and down in elevation, and the other which can move it horizontally around in azimuth. Okay, and with that combination of these two motions, you can point it in any direction in the sky and keep following it as the earth rotates. Okay, And so we won't go into too much of the details, but these are the different ways in which you can bring the signal to the focus and pick up the final electromagnetic wave and convert it into a voltage. And these are the different kinds of antennas with different focus arrangements. And this is just, you can see different examples of radio telescopes around the world. And then there is the thing that in order to reflect the waves, as we discussed, the surface has to be parabolic in shape. Okay, but then you can ask what should be the surface made of. Okay, so you will say, well, it should be a reflector, right? Because it has to reflect. If you put rubber, rubber will not reflect electromagnetic waves. Metal will reflect electromagnetic waves. But you can ask, does the metal have to be a solid metal? Can it be metal with perforations? Can it be a metal with some mesh? Okay, so there are various ways in which you can make this, and you can ask what works. Okay, and so what works, then you go to a simple principle that in order to make any surface act like a reflector for certain wavelengths, the minimum filling factor in that surface, it depends on the wavelength of the radiation. Okay, so if you had a very coarse grid or a mesh, then low frequency waves will bounce back and reflect, but very high frequency waves will go through it. It will look like a porous surface for it. So the analogy to this is, if you have a net and if you bounce some balls on the net, then if the balls are smaller than a certain diameter, then they will go through the net. If they are bigger than a certain diameter, they will bounce back from the net, right? And so you can think of the size or diameter of the ball as the wavelength of the radiation. So if the wavelength of the radiation is very short or small, then that wave will go through the mesh, otherwise it will reflect. And so depending on what frequency at which you are operating, the antenna can be having a mesh like this, or it will be a solid reflector. So if you go to very high frequencies or short wavelengths, antenna has to be a solid surface, otherwise it will not reflect properly. And but if it is otherwise, then the antenna can reflect. So in the GMRT we have low frequencies mostly, like around 1 gigahertz or 30 centimeter wavelength, as compared to this kind of antenna which is working up to 100 gigahertz and a shorter wavelength, and therefore it can it needs to be a solid this thing. Now one of the interesting things is that if you have a solid antenna versus a antenna which has a mesh for the reflecting surface, obviously this one will be lighter, right, for the same size, because it's mostly porous, whereas this is all solid metal. But there's one more thing which I'd like to ask you, that there is one more big difference between something which is a solid and something which is a mesh in terms of so you can see, for example, that this one has a much heavier structure behind it to support it, and this is a much lighter structure to support it. And besides the weight, there is one other big factor. Anybody wants to take a guess what makes a big difference for something which is a solid surface versus a mesh?
So in the solid surface, okay, in the mesh, I mean, I wanted to ask that this reflector also contributes to filtering. Now, this antenna with mesh already works as a filter, I guess, for higher frequencies.
Yes, that it does. The higher frequencies will pass through. That is correct.
That won't happen in the high frequency antenna because they will also detect lower frequencies.
Yes.
At least the reflector level.
That's correct. It will reflect the low frequencies also, as well as the high frequencies for which its surface is good enough. That's correct. But you know it. So you could use it for low frequencies, but most of these are designed to optimize their performance at the higher frequencies, because that is why people have gone to the extra effort of building a solid surface and so on. But one big difference between a solid surface and a mesh is that a solid surface offers much higher resistance to wind. right? So if there is wind, which is always present, wind will act as a force on the antenna, right? So and this you would have seen. So when you go, you see banners put up, right, in the city all the time. The ones temporary banners, cloth banners, you would have seen, right? And you would have seen that the smart people who put up cloth banners put small holes in the banner. Have you ever noticed that? And so the banner which is put up with small holes lasts longer up there than a banner which is people put nice banner and don't put any holes and they mount it, and you find that that is the one that will come down the earliest. Why is that? That is because when wind is blowing against it, then the wind force will be maximum if you have a completely solid surface, right? And the moment you perforate that surface, a good part of the wind will go through and less of the wind will actually, so the total force on that object will be less. So if you are to support it from behind, then your support structure does not have to be so sturdy in the case where the surface is perforated, as compared to the situation when the surface is completely solid. So in all of this you have to support the structure, right? So when the antenna is up looking like this, wind is blowing against it, this structure behind it is meant to keep it steady, right? And so in this case you have to use much stronger support to keep the antenna supported, whereas in this case a much lighter support structure will be able to support the antenna, because a lot of the wind resistance is nullified because of the design of the porous mesh. So that's the reason why, besides the fact that it is lighter and cheaper, it is the entire support structure. And then finally you have to move this, right? So when you move it, the heavier the antenna, the more complicated is the drive system, because it has to move with the same precision sort of, but the heavier antenna with more wind force will require a more complicated machinery to move it. Okay, so this kind of a thing is the way it works. It depends on what frequency for which you are building the antenna and what you are going to do with it. Okay. And this is an interesting thing that I was saying, that you have to have the antenna which can move in two axes to follow, but there is something called equatorial mount. So you understood why we are following objects in the sky, because the Earth is rotating, and the Earth rotates around a certain axis, right? So if you had one axis of your antenna aligned with that rotation axis, then you just have to move the antenna around it to follow any object in the sky. Okay, so for example, if you build an antenna like this, where this axis is fixed, then the antenna has to, for a given source that it is pointing to, it just has to keep moving to follow the source, because the source will make a circle around this axis, which is the parallel to the axis of rotation of the Earth. But if you make a general antenna with two axes, one vertical, another horizontal, then in order to follow, it has to move around both the axes in order to follow an object in the sky. And so these are then more complicated drive mechanism. This is a much simpler drive mechanism, but in order to do this, you have to build this extra thing where the whole antenna is supported at this angle on one axis. Okay, so now we'll come to one last part which we can link to our original thing about the sensitivity and the resolution. So all this time we were building these bigger antennas and collecting more signal over larger bandwidth, reducing the noise. All of this was to improve the sensitivity, right? And sensitivity, if you remember, is the ability to detect the faint signals, and that was our challenge, that all the signals coming from the celestial sources are very, very faint, and you need to have the instrument with the right capability to detect them. But if you remember, there were two things that were important which went with the size of the antenna. One was sensitivity, the other was the resolution. Okay, and you remember the resolution, when we talked about it, it had two terms. One was the lambda, the wavelength of the radiation, and the d, the diameter of the antenna, right? So now when you calculate the resolution for the radio antenna, then you find that it is much poorer compared to optical antennas, even for the same size of the antenna. Why? Because the lambda is very much different, right? So, if you know the frequency, how do you calculate the wavelength? Right? So, they are related by the speed of light, right? Okay. So, for example, if you have a radio frequency of 300 megahertz, then it will be like a 1 meter wavelength. Okay. Whereas one of you gave the answer, right? The optical thing is of the order of hundreds of nanometers. Okay. So, between hundreds of nanometers and 1 meter, there is a huge difference. Okay. So, one of the optical wavelength is much smaller than the radio wavelength, which we saw in that first diagram where we showed the entire electromagnetic spectrum, right? So, what that means is that even if you have a 100 meter size antenna with the 1 meter size wavelength, the resolution is quite poor. It is only about half a degree. Okay. Now, what is half a degree in the sky? If you look at the moon and the sun, they look roughly the same size in the sky, right? Physically they are not the same, no? We know that moon is a much smaller body and the sun is a much larger body, but in angular dimension they look about the same. That's roughly half a degree, 30 arc minutes. So it means that your resolution of a 100 meter size antenna operating at 300 megahertz is just about half a degree. So you say, well, which means that if you put that antenna and look at the moon, you will not see any details on the moon. It can't resolve that. Okay, it can only see objects which resolve objects which are like 1 degree apart from each other. Okay, so that is much poorer compared to the optical telescope. So the optical, you remember we saw this picture. The optical telescope shows this kind of image of the moon. Corresponding radio telescope will show you some blurred image like this. You can't make out any details. So that is obviously not good. Okay, because that means that so it is like saying that I can see the bones with the X-rays, but the bones are just one solid mass. I can't make out whether this is the lower part of the bone in the leg or this is the upper part of the bone. You can't make out the details. Okay, then you say, well, this is not very useful. Okay, so you have to now ask, what do I do? And you know that it is just lambda by d, so I must make d larger and larger in order to get better resolution. So you say, well, can I make d much larger? So this is like a 100 meter size antenna. 100 is huge. Okay, 100 is much bigger than the size of this auditorium, for example. Okay, and it is fully steerable. So that is a very difficult job. It becomes very heavy, very expensive to build such antennas and maintain them. In fact, this is one of the biggest antennas, 300 meters. Okay, but 300 meters, it's becoming like half a kilometer kind of thing. There is now a bigger one in China, which is about half a kilometer. But these are so big that you can't move them. Okay, so they are fixed in the ground, which means they can only look at some particular direction in the sky. And as the Earth rotates, some object will go through there. It can study that object for a short duration. Okay, so these are not very general purpose antennas. Okay, but still people do build these because they have some value. They will give you a good resolution and obviously very high sensitivity because it is collecting so much signal. Okay, but it can't be very useful. Okay, so this is another example just to show that same Andromeda Galaxy with good resolution. With poor resolution, it will look like this. It will just be a blurred object. So this is what you want to improve. Okay, so what was realized in radio astronomy quite some time back is that what you can do is, instead of building one large antenna, you build many smaller antennas and put them at larger distances, and then combine the signal from all of them in a proper manner. Then you can synthesize effective antenna whose size is equal to the largest extent of this array of antennas, okay, as far as the resolution is concerned. So now you say, wait, what happened? This sounds like a bit of magic, but then there is a technique behind this, whereby you can actually show mathematically that you can recover the resolution of a antenna whose size is ds now, where ds is the largest separation between the antennas rather than the size of the individual antennas. Okay. So this allows radio astronomy to become competitive as far as resolution is concerned, because now you say, well, this is easier. I just have to I have to have enough land where I can put these antennas. They need not each of them be, kilometers size antenna, but their separation can be kilometers. But then the complexity is replaced by the complexity in processing the signals. So now you will be getting signal from all the antennas. You have to bring it to a common place. You have to combine it in a proper manner as per the mathematical theory, and then be able to synthesize the signal as you would have got from a larger antenna. Okay, so that becomes a complicated piece of electronics and signal processing, but that is still cheaper and easier than building a huge mechanical structure which is kilometers in size and using it for doing the observations. And you can achieve comparable resolution. Now, for those of you who are more in college and so on, this is actually comparable to Young's double slit experiment. Anybody has done the double slit experiment or studied it? Yeah, right. So in a double slit experiment, you have two sources of light and you get interference pattern, right, which is like a sinusoidal interference pattern. So and if you change the separation of the slits, the frequency of this pattern changes, right? So in some sense, that is how any two antennas out of this array are working. It's gone off again. There it's back. And basically, it acts like a spatial filter. It will basically, if you think of image, I don't know how many of you have studied Fourier transforms and other kinds of things, but you can decompose an image in the Fourier domain, in Fourier transforms, and this is actually assembling the image in the Fourier domain, and then you can do an inverse transform to get it. So, but let's not get into all those mathematical details, but what it shows is that you have to add extra complicated electronics behind it in order to process the signals and get the final answer. But when you do it, you can get a very good resolution. So now you can see this is an image made with one of these array telescopes, and now you can see the meaning of resolution. You can see now much finer details in this radio galaxy than you could do with an image made with the old traditional smaller single antenna telescopes. Okay, so now you can ask, well, if you can do this, if you can have antennas which are a few kilometers apart and connected, can you extend this? So for example, if I put one antenna at one end of the country and another antenna or at the other end of the country, will I get a resolution which is equal to the size of the country? Okay, and so in principle the concept is yes. So for example, there are arrays where antennas spread out over the entire continent, and you can get the resolution of a single aperture whose size is as big as this, which is huge, right, which is thousands of kilometers. Okay, but you say, wait a minute, how do you do this? How do you get the signals from each antenna together? How do you do the combining? There is technology how to do this. Okay, in the earlier days, what you used to do is you would record the signal locally at each place, carry the recorded media, whether it is tapes or even hard disks, to a common place, play back the signal, and then do the analysis. Today, with optical fibers, you can connect even faraway antennas, even thousands of kilometers apart, and bring the signal together to a common processing facility and do the computations that are required in order to do this. Okay, so this is called very long baseline interferometry. It's possible within a continent, it's possible between continents, and so on. And you can ask, well, if this is possible, then is it possible in this manner, which is between Earth and space? Okay, and this has also been done, that you have antenna flown, again like we were discussing earlier, for other wavelengths where radiation does not reach us, that you put it on a rocket, send it on a satellite, and you unfurl the antenna, and it is orbiting tens of thousands of kilometers from the Earth, and it is observing the same source that these antennas are observing. They are both picking up the signal. Again, the same problem, you have to bring the signals together. Okay, so whatever equipment you use for the downlink, so the signal that is recorded here is transmitted on the downlink to a receiving antenna, just like now your satellite dish kind of a system, and this signal is then combined with the other signals picked up by the Earth based antennas. Now you have a distance which is, so now you can get a resolution which is even finer. So this is really useful for seeing very compact objects where you really want to separate out, like at the very core of a galaxy, there's a black hole and there's a jet coming out. Then you want to see exactly what are the fine details. So now this goes down to resolutions which are milli-arc seconds, okay, which is much finer than this half a degree 30 arc minutes that we were talking about earlier. Okay, so now you can see the whole sort of range and scope of how sophisticated or complicated a radio telescope can be, starting from a simple single dish. Okay, and all of these are done at various levels. And what we'll do is we'll just end with a quick look that a total radio observatory, what all does it contain in order to make it work, and we'll just go to our own observatory. Has any of you been there? Yeah, okay, good. So at least some of you have seen it, and I hope that after listening to this, more of you may be motivated to go and visit. It's not very far. It takes about 4 to 5 hours from here to reach GMRT, and we welcome people who want to come and visit, whether it is students or just the general public. And so it is one of the largest low frequency radio telescopes. So low frequency means the lower part of that large electromagnetic window, radio window that we saw, and so we work in this range from around a bit closer to 100 megahertz to around 1450 megahertz, and it was built during the 1990s and has been operational since 2002. There are 30 antennas, and each antenna is not small, 45 meters in diameter. So 45 meters is certainly of the order of the size of this auditorium, bigger than that, and 30 of these are spread out over roughly a diameter of about 28 to 30 kilometers. So which means that when you combine the signals from all of these, you can synthesize an antenna whose resolution is that of a 30 kilometer size antenna. And so this, I don't know why it does keep going off, but this is it is an array where 18 of the antennas are in a Y-shaped structure, going out largest distance a bit over 14 kilometers, and 12 antennas in a central compact 1 kilometer by 1 kilometer region. And so I said you can get a resolution of almost a 30 kilometer size antenna. So if you go ask Google to show you what GMRT looks like, this is what you will see. So this is a Google image of the central 1 kilometer by 1 kilometer region. You can just about make out individual antennas as these white blobs. You can zoom it, and you can now start see actually the antenna shapes. These are the three closest antennas, these three, and this is the Google image of the maximum zoom, and you can see these very clearly. And this is the main receiver building. So the signals from all the antennas, they are brought over optical fiber, and they enter the receiver room over here, where they're converted back to electrical voltages and all of the other signal processing that is needed in order to combine from all the 30 antennas to make the final image is all done over here. There's a control room over here from where you can control the entire array and do everything. Running an entire observation and collecting the data can be done from there. And these are the rest of the facilities that are available in the building, guest house, and a lot of the labs where the engineering team works, who have designed these things and have built it and run it. Most of the people work over here. and this is about it's about 80 kilometers from Pune, a little bit longer from here if you go. So this is a view from nearby hilltop where you can see a large number of those central square antennas whose Google image we saw a short while ago. This is a close-up of one of the antennas. Now this gives you this sense of what 45 meters is compared to the size of this truck, and this is a special high lift platform that is needed in order to access the focus point of the antenna, because this is the place where the first electronics is there, that feed antenna which converts the electromagnetic wave into electrical voltage, and the most crucial low noise amplifiers have to be right up there before the signal gets corrupted by noise or unwanted signals. And so a lot of the most sensitive electronics is right up there, and then a certain level of amplification afterwards the signal is taken down on cables, electrical cables, which bring it down to the bottom over here, and here there is further electronics for more amplification, filtering, and then converting it onto a signal that can be sent on optical fiber, and the optical fibers then go from the antenna all the way to the central building where the received optical signal is converted back into electrical voltage, and then the combining from all the 30 antennas happens. So just to give you a sense for what it is, this is a typical the construction sequence of one of the antennas when they were built in the 1990s. And so this actually is a 3-story building, equivalent height, on which the antenna sits, and the total height at this point is about a bit over 30 meters, and that's what that crane is specially designed to do this. So the whole antenna was assembled on the ground around the tower, and then lifted up, and then mounted in place over there to make it work. Okay, and so you can see that in order to make such an observatory work, there are various parts of it which need to be there, from mechanical to servo. Servo is the thing which will move it in a precise manner, the entire gears, drivetrains, motors, and so on. And then all the electronics of different kinds, from radio frequency electronics, these are these feed elements which pick up the signal and convert it to a voltage. From there to the entire receiver chain, the high quality amplifiers, the precisely done filters, the optical fiber technology to transmit all these wideband signals back, and the digital technology to digitize the signal, process it, do the combining of all the antennas and all of that, and then the telemetry command control, because this is like a remotely controlled observatory. You sit in the control room and you send commands to all the antennas to do all the operations, from moving the antenna, tracking a source, to configuring all the electronics, what frequency it should be observing. All of that can be done sitting in the control room, and you can monitor everything. Did it work? Is it pointing in the right direction? What is happening? Has something gone wrong? So all of this requires a very sophisticated monitor control system. And finally, when you get the data, you have to still process it to make the image that the astronomer can use. And so there's a lot of software and image processing that happens downstream when you get the data. So this just tells you that there's a whole whole set of technologies and engineering and ideas and concepts that are needed in order to make this thing work like a proper observatory. Okay, so I'll not go into the details of this because this gets a bit technical, but anybody who's interested, I can talk to them later to explain how this, the basic ideas of the electronics and the different parts of it. And I'll just go on to say what has been happening. So like I said, it was built during the 1990s and it was inaugurated around the end of 2001. And since 2002, it has been used and available to the worldwide community for astronomers to use it. And you can ask, how is it used? So if you are an astronomer anywhere in the world and you have a bright idea that this kind of observation can be done with this radio observatory, you can write a proposal and submit it. Okay, and these proposals are taken. We have 2 windows every 6 months to take proposals from anybody in the world. The proposals are reviewed by a evaluation committee, which consists of experts, and those experts can in turn refer or call on any other expert in the world to get their view on a particular proposal. So they will evaluate all the proposals as to, is this a good experiment, what kind of science or discoveries it may result in. It will give them some ranking, and then it will give a recommendation that this proposal is good, it should be given time on the telescope, and this experiment should be done on the telescope and this particular source or whatever they want to do. Okay, and the proposals come from all over the world. So you can see that about 50% of the users are from different countries in the world, something like 15 to 20 countries, and about 50% of the users are from within India, from different institutions in India, including our own scientists from our own institute. And in any kind of a situation like this, now you can imagine that this becomes a demand and supply situation. So there are so many requests that come in every 6 months, and people say, I want to do this experiment, somebody says I want to do this, and somebody wants 10 hours of time on the telescope, somebody wants 100 hours to observe on the telescope, and so on. And you add it up and you say, well, I don't have so much time in 6 months. Okay, you have only 180 days into 24 hours max that you can have, out of which some of it goes into our own maintenance and upkeep time and so on, but the telescope runs for a very large fraction of the 5.5 months. But still you have more requests than you can handle. Okay, and this is called oversubscription. And what does that mean? That means that those who are the best ideas, and that is what the review panel or the evaluation committee is supposed to do, is to look at all the requests and say, well, rank them. These are the best, they should get the highest priority, and these are less priority, and the ones where they say, sorry, this is not good enough to be given the time. And so typically that oversubscription is about factor of 2.5 to 3. So there is that much of cutting that has to be done from all the requests that come. So if you could put a request, or you have an idea, make sure it's a good, bright idea that will beat most of the other ideas. Otherwise, you will not be guaranteed to get time for doing your experiment on the telescope. Okay, and then you say, well, you've told us so much, but what are these things that people do with the telescope? Okay, and so there are different objects in the universe that you can observe. I won't go into the details of this, but like I was saying earlier, we observe the sun primarily through optical waves, but the sun emits all kinds of radiation. Okay, radio waves also. So you can study the sun with radio waves, and you can get a very good idea of some of the physical properties of the sun by doing radio observations. You can actually look for extrasolar planets. Today you hear extrasolar planet detection is a hot topic, and so many planets are being found. Most of them are found in the optical by these telescopes like Kepler and so on. But it is possible to search for extrasolar planets using radio waves. And then pulsars, which is what the next lecture will be about, so I won't talk about it here. Then other galactic objects, supernova remnants, microquasars, and explosions in the galaxy, gamma ray bursts in other galaxies also. And then hydrogen in various ways. So I think most of you will know that hydrogen is the largest constituent of the universe. A very large fraction of the universe is hydrogen gas, either neutral hydrogen or molecular, as atomic or molecular hydrogen, and this occurs in large clumps or clouds, many of which are present in our own Milky Way galaxy. So a good fraction of any galaxy is made up of clouds of hydrogen gas, and that's one of the best ways to study a galaxy. And it so happens that neutral hydrogen emits a signal at 1420 megahertz, which is right in the radio frequency band, and you can detect that quite easily, and you can use that to probe the structure of our galaxy, the structure of other galaxies, faraway galaxies in the universe, all of that using this neutral hydrogen line. Okay, so this is one of the powerful things that radio astronomy offers. And then many galaxies are very bright in radio. So again, it goes back to our picture of the Milky Way, where it is bright and optical, it also has radio, but also this concept that I told you, that some objects shine only in certain wavelengths. So there are certain galaxies which are very, very bright in radio, and they are very faint in opticals. If you look with the good optical telescope, you may not detect them even, but they just stand out when you look with a radio telescope and you say, oh, I didn't know there was this kind of a galaxy also in the universe. And there are many such galaxies. And so that gives you a different view, a different perspective of the universe when you look at those with the radio telescope. And you can see them to very large distances of the universe, to the very early stages of the universe. And some of these experiments probe the very early times when the universe, when the first stars formed, when the first stars turned on and started ionizing the neutral gas in the universe. All of this can be probed through the radio window. And you can also make all-sky maps. So, you know, like an atlas, you have an atlas where somebody has nicely made maps of every country in the world in a uniform manner, showing you all the cities, all the valleys, all the rivers, all the mountain ranges. Okay, so, and you use that atlas to extract general statistical information. For example, if you want to know, you know, what is the total amount of land mass in mountains in a certain country, you go look up the atlas, you can get that information, right? So in the same way, people do make atlas of the entire universe. So when you look around and you say, in a uniform manner, I will scan the universe as that I can see with my telescope, and I'll make a map which is like an atlas. So there will be pages, just like an atlas has pages, showing you this piece, then this piece, then this piece, and so on. Some of you may have seen these, if you're into amateur optical astronomy, there are optical star atlases, you know, which are literally like maps which will tell you, if you look in this direction, this is the constellation you will see, these are the stars, these are the nebulae, and so on. And these are, so these have been done in at frequencies which were not done before by any radio telescope and are available as information in the literature which scientists use for various kinds of studies. Okay, so I think I'll stop here and say that this GMRT, which we have been running for now well over 15 years, we have recently upgraded and improved its capabilities by improving the quality of the electronics, the range of frequencies it covers, and so on. And it is a much more improved telescope which has kept its position as one of the most sensitive radio telescopes in the world, and we are hoping that it can be like this till the next 5 to 10 years, at which point this square kilometer array, which is one of the main reasons for having this mega science exhibition, telescope comes up, where India is a part of that project. And I don't have time to go into the details of that, but if you go to the main pavilion, you will see the exhibit of SKA, which talks about what is India's contribution in that project and what we hope to do when the construction of the telescope starts. So we're just finishing the design of the square kilometer array. By the end of this year, the final design will be done, and sometime about end of next year or early 2021, the construction of the telescope will start. It will be located in South Africa and Western Australia, which all this information you can get in that pavilion over there, and which are the and so you can ask why there. So, you know, one of the things we talked about that, and this is how radio astronomy was discovered, by looking for unwanted signals in the transmission equipment. So you can think that when we observe, do we get any unwanted signals in addition to the noise from our own electronics? And we get lots of unwanted signals. And so the same thing, so if you go to GMRT, you'll be asked to switch off your mobile. Okay, you won't like it, okay, but for the duration that you're there inside the observatory, no mobiles. Why? Because that power that your mobile transmits when it talks to the station and vice versa is so strong that it is much stronger than these very weak signals that we are looking for. And so when you want to build the best radio telescope, finally you want to put it in a place which is far away from all of us. Okay, so far away from mankind, man-made activities, so that all these disturbing signals can be minimized. And so And now today there's not too many places on the earth where you can do this. Okay, so when GMRT was built in the place where it is, there were no mobiles. There wasn't that much of all the activity, but all that has come and it will keep coming. So today people go to find places where the number of people per square kilometer is like 1 person per square kilometer. Now you cannot imagine any place in India where you will have 1 person per square kilometer, right? Bombay is how many millions over a few square kilometer, right? So, so you need to go to places where you are not disturbed by man-made radio noise and radio signals, so that you can get the cleanest environment for the radio astronomy study. And these are all places near semi-desert regions where there's not too much human population. And if you go and look at and there are a couple of other constraints, that the quality of the ionosphere above, because ionosphere can affect the radio waves. As we saw that at the lower end of the radio spectrum, ionosphere starts cutting off. But even in the frequencies that we operate, ionosphere can disturb the propagation of the radio waves. So you need to go to places where ionosphere is stable, less active. So so all of this takes these facilities to places which are remote and convenient for radio astronomy. And so that is where all the next generation very large radio facilities will be coming up, and the square kilometer will be like that. And India is looking to be an active partner in the work. We have been actively involved in the design, and again, if you go to the main pavilion, you will see what work India has done during the design phase of the SKA, and you'll get a flavor for what are the, like I showed you, in any radio observatory, there are all these various technologies that are needed, and in the SKA you need them at a much higher level, and there will be some of the areas that we will be looking to participate during the construction phase. And of course, the idea is that our astronomers and scientists should be able to get access to the telescope to be able to do various cutting edge science experiments and research for understanding different aspects of the universe using the radio waves. Okay, so with that I'll end my introductory talk. Anybody has any questions, anything that they would like to ask? We can discuss for some time. Yes, you came in late, but you have a question. Yes, go ahead. Say it again. Some particular.
Do they use some materials that reflect the particular frequency when they are around the telescope, so that the mobile or thing that emit towards a particular frequency radio waves get reflected?
Yeah, so that is correct, that we do use the certain design of the radio telescope to reflect the radio waves. Okay, and in that design is included the choice of what you use for the reflecting surface.
They are not saying that.
Yes, okay.
Something around the radio telescope.
Oh, nearby, around it.
Yeah, so that mobile phones cannot.
That is difficult because for two reasons. So what we sometimes do is that, and if you stay around for the afternoon talk, which will be given by my colleague here, he will actually talk about interference and how we try to block it. But what we do is we try to get the mobile transmitters to modify the way in which they transmit, so that less of that signal reaches to the radio telescope. But once it reaches there, it is very hard to block it from reaching the antenna. What we try to do is to minimize the amount is emitted. So I'll give you one example, and he will probably show you more examples in the afternoon talk. So it is not just the mobile, even anything that has a discharge produces electrical signal. Okay, so if you look at, for example, tube lights. Okay, tube lights have a discharge whereby the final light is produced, and that has an electrical discharge which can produce interference, because it's like anything which sparks produces interference. Okay, and even LED lights have the same problem. Only the old-fashioned halogen lamps, which are just glowing because of the heated filament, there is no electrical discharge. So traditionally we always use those, but now it's harder to get halogen lamps, and they are much more energy inefficient, as you all know, and everybody wants to use LEDs and so on. So when we use them, we have to take special care to reduce the amount of unwanted emission that they produce. And so these are the kind of things that we do. But once it gets into the antenna, it's hard to block it. There are a few things that can be done, but once it gets inside, there are other techniques that we try to use in order to remove that signal or filter it out. You can't always do it, but wait for the talk if you want to understand more how this is done vis-a-vis blocking unwanted signals. Okay. Anybody else has any other?